This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello everyone, this is Felienne for Software Engineering Radio, and today I have on the show with me Adam Barr. Adam Barr has worked as a programmer and manager at Microsoft for more than 20 years, and he's the author of several books about programming, including Find the Bug and Proudly Serving My Corporate Masters. Welcome to the show, Adam.
Thank you, glad to be here.
This show today is going to be about your latest book that I've just read with great interest called The Problem with Software: Why Smart Engineers Write Bad Code. And this is, of course, also what the book is about. So can you tell me more about that? What in your view is good code or bad code, and what distinguishes between the two?
Well, it's a problem in the software industry that there really is no idea of what good and bad code is, except much later if the code has bugs or it's hard to modify. So it would be nice if we could figure out while writing the code or soon after whether the code was going to wind up being good or bad. That would save a lot of time. But right now people just think code is bad if it doesn't look like the code they would personally write, but a lot of those guidelines are based on their own experience and they're very anecdotal. So you get these code review arguments which are just about my coding style versus your coding style. And the reality is any code that somebody just wrote probably looks fine to them because they understand that they still have the mental model in their head. So these arguments about good code are really about two people debating something with very little actual facts behind them. And that's why you get these disagreements over things.
Yeah, because there are ways that people try to measure good code. Yeah? You already mentioned coding styles, but there are different tests as well that people use to measure if code is good, like cyclomatic complexity. Do you think that makes sense? Is there a way to measure code quality, or is this all?
There is nothing that I've seen, even something like method length, what's the right number of lines in a method. So I've heard people say that almost any low positive number, I've heard somebody say, oh, that's too long. If you have 10 lines of code, that's too many. If you need a comment, that's too many. You need to immediately split the commented section into another method. Steve McConnell, when he was writing Code Complete, actually studied empirical research where he could find it. And the number he came up with, I think the number he found, was about 100 lines is too long, which of course I think is way longer than people are actually claiming now is too long. The problem is you start to split your code into too many small methods and it's hard to track the logic through the code. So there probably is a good number for something like method length, but nobody really knows what it is. And if there was research on it, people probably wouldn't be aware of it. Cyclomatic complexity is another one. It's probably good to look at your most complex methods and figure out what's going on, but there may be valid reasons why it's better to have the method be complex than to split it up into a bunch of smaller methods, which is essentially the alternative. So I think these metrics are useful to give you code to give a second look at, but there's no real standard on what's too complex, what's too long, that sort of thing.
And the things we talked about so far are all internal code quality. So you look at the code and you see if it looks nicely. But of course, there's also something like external code quality. Does it even matter if the code is badly structured, if the tests just run, if we have enough tests and it does what the user wants it to do?
Yes, it absolutely matters. Everything, when people talk about code reviews, good code, bad code, they're really trying to anticipate the future. They're essentially saying, I think this code will be hard to modify in the future because it'll be hard to understand and it's not readable. That's really what they're getting at. And that's critically important. As I said before, almost any piece of code you can get working in almost any language if it's just one person working on it and they wrote it last week, they'll remember how it works. The real problem is in the future when people modify it, when it gets modified to work on for some different purpose, which inevitably happens when people who originally worked on the code are no longer working on it. Fred Brooks, who was a person who wrote, or is a person who wrote a lot of important articles about software engineering, made this differentiation between a small piece of software that a few people worked on for a short period of time and a software product which was worked on over the years by different people. The team would change and it would be a bunch of different components merged together. And really, when you're talking about code quality, you're worried about the second one. When it's not the original authors, when you have multiple people working on it or multiple groups of people working on it, will they be able to understand it? So it's absolutely critical that the code be readable and understandable, even if the tests pass, even if today it works fine for the customers.
So I think what you were saying is that for you, the definition of code quality is if code is easily modifiable, if it's easy to change. Is that correct?
Yes, if it's easy to understand and change, and the reason people want to understand code generally is to change it. So yes, it's, to me, the most important thing is, can it be modified without breaking it accidentally or just because it's too complicated to touch without something breaking.
Yeah, you already mentioned this a bunch of times in the interview so far, that there's definitely a difference between small teams working on small products and big teams working on big pieces of software. And this is also one of the topics that is quite prevalent in your book, is about how people, when they learn to program, often when they're teenagers, just doing it when they're in high school, they really get used to this one person development team that's just them. Can you talk a little bit more maybe about your experience growing up and what things you learned when you were learning to program when you were younger?
So that was exactly my experience. I taught myself to program. This is in the early 1980s. So first in Fortran and then in BASIC, IBM PC BASIC, we had a very early IBM PC model. So you're writing very simple programs. I would write simple games. And when it's just you, even a language like BASIC or Fortran is fine because you understand what's going on. It turns out that in retrospect, Fortran and BASIC are terrible languages. For large scale development, the versions back then didn't have methods with parameters and local variables and or if blocks, so you could actually have a block of code after an if. Very basic things now, but they didn't have them. So you learn to write what they call spaghetti code with lots of go-tos and global variables. And you thought it was fine. You got it working. You were the only person working on it. So you thought, oh, this is great. And then when you got to larger companies and you had to work with other people and design APIs that work together, you didn't have any training. You thought, oh, I know everything about programming. Look at this awesome game I wrote when I was younger. And unfortunately, Microsoft was, when it started, almost entirely populated with people like that. People who had taught themselves to program on their own and thought they knew everything about programming. And although they were smart people and they got things working eventually, it caused all kinds of grief because people really didn't know how to work in large teams and write software that was maintainable.
Yeah, so let's talk about those all kinds of griefs. What are some of the bad habits that you picked up when you learned to program on your own that you later had to unlearn as a professional developer?
Well, the biggest thing probably was just being able to design an API. So really think about, I'm writing this code, but somebody else is going to consume it for use because software tends to be layered like that. So I have to make the API clean and understandable, not just what I think is a nice API to provide, but what would be a clear API for them to call. And I have to document it well and all that. So I just have to think really about, I'm writing this software not as a mental challenge to myself, but as part of this group of components that are going to be stitched together. And I really did think about the interfaces. The other thing I had to learn eventually, was that people doing code reviews are not there to be malicious. They're not trying to insult you or your intelligence. They're actually trying to make the code better and understand it. And I think that's a little tricky again when you've always been working by yourself or in small teams, very small teams in school, that really taking criticism is always difficult, and a code review feels like criticism, but it's very important for the overall quality, both for making sure you don't have problems with your code and also for other people learning about your code. So I think if you could, that part is something I talk about in the book, which is programmers need to be a little humble. They need to not think they're the greatest programmer in the world. And unfortunately, you get a lot of people coming out of college thinking they are awesome programmers because they've been able to teach themselves to program, be successful in college with those self-taught skills. And when they get to industry, they're really not ready to accept the more learning they need to pick up, the other set of skills they need to be a successful programmer working at a company on a large software project.
Yeah, we will definitely get back to the teamwork and the humbleness later in the show, but for now I want to focus on the source code itself a little bit more. So one of the tips you already gave was you have to, if you want to write maintainable code, you have to think in interfaces. What is a good API structure? How are people going to use my source code? That seems like an amazing tip. Do you have any other concrete tips? How do you make code if you start working in a team that your teammates will not hate?
Well, I think the other thing, you need to read a lot of code. Somebody once made an analogy that to be a good cook, you have to eat a lot of food before you start cooking food yourself. It's the same thing. It's another benefit of code reviews. You need to read a lot of code. You need to appreciate other people's style, realize that your style may be different, but there's reasons why people write code with other styles. And so it's something I talk about in the book, that I I'm hopeful that universities can start exposing people to large code bases, exposing students to large code bases, so they could really understand how large code is structured, and as I said, just learn to appreciate that there's different ways to write code. So when you work on, even in university, working on 2 or 3 people projects, which is better. I did a lot of solo projects or with 2 people, but now I know a lot of universities work on 3 or 4 people projects. But it's one semester. The code goes away once you get the grade, kind of thing, and so you still don't really learn to work in large code bases, and you tend to know the people you're working with. You've worked out the design yourself, so it's still basically a fairly simple project compared to what you do in industry.
Yeah, so you say read a lot of code. That seems also good advice, but how would I go about this? Imagine I am a new programmer and I want to learn to read code. What would I do concretely? Like go on GitHub and read a random project? Are there specific strategies you could recommend?
Well, this is actually a huge thing that's changed since I was learn teach myself to program. So back then, there really just wasn't large code available to read because there was no internet, and you could you. I used to read these books, these basic microcomputer games books, and they had listings. They might have a 4-page listing of a computer game, and you'd
Yeah.
actually type it in, and that was about the biggest piece of code you could see. And then if it was still pretty short, you'd maybe have to modify it a bit to get it working. But now you have open source, and you have these projects that you can read. At least you can make local modifications. You could even contribute back to. So yes, it's essentially go to GitHub and start reading code, but you could pick some component that you use or you're interested in, or some area of computing that you're interested in. But yes, essentially do that. Go on GitHub, go find some open source repository and pick something you're interested in and try to understand it. Figure out, if you can't understand it, what it is about the code that makes it difficult to understand. You could probably contact the author if you have questions, because really when you come to work in industry, that's what you'll be doing for the vast majority of the time, is modifying existing code, fitting into existing systems, not writing greenfield projects, these brand new projects that you tend to do when you're in college or working on your own.
And you also said that if people start reading source code to learn more, they should appreciate a lot of different styles. What are the styles you're talking about? Is this imperative versus functional, or different programming languages, or?
Well, there's that too. Of course, you could read different languages. People have this tendency to learn one language and then decide they can solve all problems in that one language. But no, it's things like method length, how you name variables, how you name methods, how many comments you put in, that sort of thing. The things that, even though they don't directly necessarily affect the functionality of this software, when it's compiled, it might all wind up being the same thing. But for readability and understandability, they're very important. So it's just reading a code and thinking, it took me a while to actually figure out what was going on here. Why is that? Is it something in the way the code was structured that made it hard to understand, or was it a lack of comments, or maybe it's just a complicated part of the code that's a little tricky? But is there something that could have been done differently in the code style to make it easier to understand?
So learning code at a young age, has also taught you bad habits like one-letter variable names. And I really recognize your story into learning programming from my own. It was a little bit later, it was in the 90s, but it was very similar. I picked up lots and lots of bad habits when I was a teenager, and I had to unlearn them when I was in university and later when I was working. Should we conclude that learning to program by yourself is a bad idea, or do you think ultimately it's still a good preparation for a computer science degree in a university?
So overall, it's a good thing, not a bad thing. We shouldn't recommend that people not program in high school if they're interested. First of all, it does get you excited about programming, even something like the hour of code, which is, of course, very, very, very simplified, but it gets people excited about programming, realizing, hey, I could be a programmer too, which is great. So, and there's this skill of just, I have a 20-line piece of code, and I know that my variables are correct at the beginning and they're wrong at the end. And so I've narrowed the bug down to this little section of code, and I have to kind of walk through it in my mind and in this very precise way, sort of simulate the computer in my mind. This is actually what my book, Find the Bug, is about. If you don't mind me throwing in a plug for that, it's about close-in code reading. So that's a very valuable skill. Just being able to debug any kind of software when it's not working is very useful. So you do gain valuable skills learn to program in high school, but you also pick up bad habits. I think the main thing I wish people knew is that you are picking up bad habits. This understanding that short, small pieces of code you write yourself are very different from what you write when you're a professional programmer. If they were just aware of that, okay, this is fun, but there's this other level, I think that would help a lot. But I think a lot of times it's presented as, oh, wow, you just did this little program. You're a programmer now. Go out and have fun. And I think other industries, people are more aware that if they put a Band-Aid on their arm, they're not a doctor. They still have to go to medical school. In programming, that distinction is, I think, often lost. And in a lot of ways, people like me sort of pulled it off for a while. We did teach ourselves to program. We're successful in university and went off, got jobs at good companies, and eventually realized that we had a big skill set gap. But after much grief, as I put it earlier, trying to figure it out and other people having to deal with us and so on.
Yeah, and there's of course also the effect, and you mentioned this in your book as well, on your classmates. And I teach at a university, as some people in the audience might know. So we get freshmen in university. Some of these 18-year-olds have never programmed, and they're welcome as well in the university. And other people in the same classroom have like 10 years of programming experience. And sometimes, indeed, in the age of GitHub, this is serious programming experience. And those experienced students repel some of the students that have less experience, that might be people from a lower socioeconomic status where they don't have access to lots of programming tools. Or, and this is something that you mentioned in the book as well, female students often are like, whoa, those other people in my class, they are already brilliant programmers. For them, the Band-Aid, I love this analogy, the Band-Aid people also look like proper surgeons. How should we deal with that?
Right. There's a great book called Unlocking the Clubhouse, which is specifically about women getting scared away from programming in university because all these high school geeks seem so confident and fluid at programming. And the quotes are really depressing when you read them about how these women are clearly very smart, but they just feel like everything is so much harder for them, and it's this insurmountable barrier. And of course, the guys also have negative attitudes and look down on them. What are you doing in the computer lab, kind of thing. So all that contributes to making them decide to switch majors. I think that you certainly want to make programming as welcoming as possible to people who have not programmed in high school, whether it's women, as you said, different economic backgrounds. There's all kinds of reasons why people might not have been programmers in high school. And so it's tricky. Schools have tried different things. Some schools they teach their introductory classes in a functional language like ML, which is strange enough that very few people will have programmed in it. So that kind of knocks the experienced programmers down a few pegs. Schools also try to focus on more interesting programming projects. So not just learning to program sorting algorithms, but actually doing something with robotics or something with games. So the end result is more interesting. It's not just geeking out on code. And there's also things that have to happen earlier. in high school, in middle school. So if somebody's trying to get interested in programming, asking questions, taking a programming class, whatever it is, they're not looked at weird because they don't fit the stereotype of a programmer. I think it's just going to be a very gradual thing. More people are interested in programming earlier, which makes it less strange, which means more people wind up majoring it, which means there's more role models to look at for younger people. I compare it to something like airline pilots. Airline pilots used to all be male, and it was a similar thing, I'm sure. If a woman showed up at flight school, people would ask what she was doing there, or try to order drinks or something. And just eventually, through more and more women becoming pilots, it became less strange. And now it's just completely accepted that women are pilots. But it took a long time to people to get over it. The other thing is something that happened is old school airline pilots retired their old school attitudes along with them. And that'll eventually happen in programming too. But programming has happened so fast. We've gone through this incredible cycle in the industry, and you still have old school programmers around who may have old attitudes about female programmers. And it's going to take some time for them to retire because it's all happened so fast compared to other industries where it took centuries and centuries for it to gradually develop and become important. Software has become critical to the whole world in 50 years.
Yeah, that's a good perspective. The newness and the changing of attitudes still has to happen. So let's move on in education a little bit, because you talk in your book about how you learn programming when you're in high school, but you also talk about your experience in university quite a lot in the book. So maybe you can summarize that as well for the audience.
Right. So I went to Princeton, which is a good school, has a very good reputation, very well-known computer science department. And what I found, and I believe this is still true since up until recently I worked at Microsoft and I would have summer interns and new hires out of college, is that universities tend to focus on algorithms because that's what professors can understand. It's very hard for professors also to work on very large scale programs because it's just one person. And so they tend to focus on smaller programs, and something you can really work on well in a small program is an algorithm. So you learn sorting algorithms and parsing algorithms, and some of this stuff is very important these days. You can work on artificial intelligence or search or machine vision, those sorts of things. But you tend to learn that in the classroom, and the classroom is not a computer lab, it's just a lecture hall. And then you're told, okay, now go write some code, go implement this. But you learn the actual software engineering part more as a byproduct of having to write this code that is something you're formally taught. So people are rarely taught how to structure code. How to debug code is a very important skill that you need a lot of when you're working, that I don't believe is typically taught in universities, how to use a debugger, how to think about debugging. And again, it's small pieces of code, so you're not learning how to write large pieces of code. You do have better languages. People tend to program in Java these days instead of BASIC or Fortran, which is a better language. It doesn't have some of the fundamental issues that languages did back then. So some things are better, but still you're essentially, even though you're going to school and majoring in computer science or software engineering, you're really kind of teaching yourself to program. You're continuing that aspect of really learning it yourself rather than being taught it.
Why do you reckon that is? Do you think because the professors taught themselves as well, they think learning is easy?
So I'm not really sure why. I don't think it's that. I don't think it's that, oh, well, I made it, I'm tough, I did it this way, so I'm going to force everybody else to suffer. I don't think it's that at all. I don't think professors think that way. But I think it's partly that algorithms is something that you can learn. One person can really understand an algorithmic area of computer science. And so it's partly that. I think it's also just that industry isn't really expecting it. So they're happy to hire all the computer science majors they can find. So there's not really this impetus to change, because if you're thinking about, I want people to be employable when they graduate, well, that's already happening. And of course, universities are not entirely focused on getting people employed when they graduate. They're also interested in research for its own sake. And I think they do tend to focus on things that one professor can do. I wish there was more empirical studies of large software projects. There used to be more of that in the 1970s. It's one of the things I talk about in my book, is that there used to be more research. People actually researched how bad go-tos were, and commenting style and variable names and indentation. I mean, all this stuff was actually researched in the 70s by academics. And essentially what happened is, around that time, the personal computer revolution began. People could teach themselves to code at home. They did, and they showed up at university, and there was sort of the interest in that kind of empirical studies dropped because people were just already ready to code, and they want to learn new stuff, and they had taught themselves without studying historical information about programming, and they just kind of continued along that path.
Well, I do think there's some academic research along those lines. We had a show about naming variables, and I myself have done some research about how do people name variables, and we can put some links in the show notes. People trying to measure, is camel case actually better than using underscores in variable names? There's some research into eye tracking and code reading, how people read code. So there's some of that empirical studies happening now, but that's maybe the happening more.
That is great to hear. I did not know about your research. Unfortunately, you can't read everything you want to when writing a book. You just run out of time. Yeah, there is still some empirical studies. There's an empirical studies journal and conference. It's still going on there. So no, that's great to hear. I wish there was a lot more of that, and I wish that students were exposed to that, to say, oh wow, there actually is some wisdom about this. It's not just my personal experience that can guide me. But yeah, I think a lot of it, the human computer interaction studies, the ACM CHI conference, which was started by empirical programmers, studies people, the human computer action, rather than being programmer to computer interaction, which is kind of how it started out, has now turned into user to computer interaction. So the studies are more about people using computers and usability and all that, and less about programmers interact with computers. But I'm very glad to hear you've been studying variable names, and yes, I'll have to go read that.
Yeah, this is all relatively recent. The empirical software engineering research has come up maybe in the last decade.
Right, but of course it was also a big thing 40 years ago. So if it's coming back, that's awesome to hear.
So you mentioned some of the skills that we should teach. This is me as well. We should teach in universities. For example, you mentioned debugging, how to use a debugger. That's absolutely something that's very important for students to learn. What other topics would you recommend that universities teach students apart from algorithms and stuff like that?
Well, I really wish they would teach language choice. So what is an appropriate language for what sort of problem? So there's a lot of talk about functional programming these days, and functional programming has its uses, but people tend to be very binary on it. They either think that functional programming is terrible or it's going to solve every problem in the world. And really, there's some situations where it's good and some situations where it's not. Or even a language like Perl. So Perl is a great language for writing small pieces of code. Perl is really great for that small project, short-term quadrant, where you don't have to worry about long-term maintenance, and it's the same people always working on the software. But then this evolves into these very large Perl programs, which are very hard to maintain. So something that would say, okay, for this kind of problem, you can use this kind of language. This kind of problem, you can use this kind of language. Not necessarily teaching the specific languages, but just the general concept that language selection is very important. And you shouldn't just use the language you used for the last project or the language you're most familiar with. Because I understand in university, it's hard to learn a language. So it's convenient to say, okay, everyone will learn Java and then we'll use Java for everything, or whatever language it is. But language choice is a very important thing for larger projects. So I wish there was more focus on that as an actual conscious choice you could make, not just a decision you slide into.
Yeah, there's actually some research into that as well. There was a guy called Leo Meyerhoff. He did a study, I think, among like 20,000 developers. He interviewed them. to understand how they decided on which language to use. And the main factors were not about language features. The most important things were, do people on my team know it? Does it have libraries that we need? Stuff like that, and not even features of the language. So this is definitely something that if people decide to use a certain language, they're not necessarily looking at features of the language.
Right. The other thing is, of course, eventually, if you're an engineering discipline, you would hope that you could decide that a certain language or a certain code base was obsolete. So there's a lot of the current problems on the internet. You get exploits, things like Heartbleed or whatever, is because a lot of the internet tools are written in C. A lot of the fundamental internet software is written in C, which is a very bad language to write network-facing string manipulation code. That's sort of like the worst thing that C can do, and that's what it's used for a lot these days. And so if you could say, this code is just obsolete, we need to replace it. We can't just keep using this stuff. But again, because it's not really studied that much and it works, so hey, why mess with it? That's another area where I wish, if we were more of an engineering discipline, since we're quote unquote software engineering, just as you can look at a bridge and say, that bridge is about to collapse, we need to replace it, you could look at a piece of software and say, that software is just no longer appropriate for what it's being used for. We need to replace it. But again, people tend not to do that.
And do you mean that at the level of a repository, or even at the level of a programming language? Because you've already mentioned a bunch of languages in the interview, saying like Fortran is a terrible language and it maybe shouldn't be used at all anymore. Do you also propose we retire some programming languages? Or is it more the combination, as you mentioned, with C, a language plus an application that shouldn't be used anymore?
Yeah, it's hard to really retire a programming language because you have all this code that's lying around. You keep hearing that there's still a lot of COBOL programmers out there, and there's still Fortran and all that. But yeah, certainly to say for new code, given this criteria on what it's being used for, who's working on it, how it's going to be run, what environment, et cetera, these languages are appropriate and these languages are not. And also a language like C has its uses, but I think that the uses are shrinking. One of the things I talk about in the book is that there's tends to be a trade-off between clean design and performance. Those two tend to fight each other. And languages that are performance focused, like C and C++, are getting to be borderline obsolete. The number of cases where you actually care about performance over clean design are getting vanishingly small, even though old school programmers who taught themselves how to program on some very underpowered personal computer might still think that performance is critically important. And, those kids today don't understand what horrible things they're causing to happen when they write this Java string manipulation code, and everybody needs to go look at their bytecode and whatnot. I think they're essentially wrong, and performance is almost never a problem, and we should really focus on the maintainability and clean design and all that. So a very performance-focused language like C or C++ really has almost no useful applications at this point.
And there are, of course, also more modern languages that focus on performance, maybe something like Rust. Do you have an opinion on that?
Well, I think that all languages, the big problem with C was the string manipulation, the using strings as arrays, the null terminated strings, which has caused vast amounts of damage. So even modern languages, they still tend to be better designed. They still can handle string manipulation well. So you can have a more performance focused language. But what I'm talking about are really these old school languages that were really allowed you to make mistakes, because it might, if you didn't allow that, it might impact performance. And so I think it's really any modern language is likely fine. It's really these very old languages, but they're still around. C and C++. Microsoft has huge code bases in C++. That's really lingering from 20, 30 years ago.
I know, I worked on such a code base.
Microsoft also managed to have some decent sized programs in Perl as well. A lot of the tools are in Perl, and that has its own problems with when used in large software. So it's not just old languages, but I think, again, something like Perl is quite useful in certain situations, but you need to be aware of when the benefits of Perl turn into negatives. The fact you can call a method with any number of parameters, of course, is kind of nifty for small pieces of code, but turns out to be a terrible idea for large pieces of code.
Yeah, you mentioned some damage done with C also in the book. And this is a story I didn't know about, so I'm hoping you could summarize it as well for the listeners. The famous Morris worm was an early example of someone accidentally making a huge mistake with a C program. Could you summarize?
Right. So the Morris worm was a buffer overrun. It was, I guess, probably the first famous buffer overrun in C. So maybe there's a bunch of people out there that aren't familiar with how C handles strings, which would be great because it would mean that C was dying out. But essentially, a string in C is just an array, and then it's null terminated. So when you get to a character 0, that indicates the end of the string. So the important thing is the language is not tracking. In C, the compiler does not track the length of an array. It's up to the programmer to figure out how much memory to allocate to store a string, and they have to count until they get to the terminating 0. So this allows this situation known as a buffer overrun. So the Morris worm was a buffer overrun in network-facing code. So you could send it network packet that was larger than expected, and it would actually overrun memory, and you could then jump into code that was inside the packet you sent and take over the computer. And the Morris worm in particular called an API that it used to exist in the C standard library called getS, which not only did it use strings, which were null terminated, so they had this problem of allowing buffer overruns, but it was an API that actually was, pass me a string buffer, don't pass the length, and I'll just start copying data into it until I see the end of a line. So it was like almost a guaranteed, like if you were designing an API to allow a buffer overrun, that was exactly how you do it. So the fact that this API existed was ridiculous, and yet it was just part of the C standard library. The fact that someone called it a network-facing code was also ridiculous. It was just an exploit waiting to happen. And yet, when it happened, the postmortems were sort of like, oh, well, that's a crazy situation. Why would someone do that? We can't design perfectly secure software, so what are you going to do? Because it was viewed as this weird situation, instead of the proper response, which should be, hey, maybe it's not a good idea to write all our internet software in C. But that was that was the attitude back then of like, well, yeah, but it can run faster in C, so, and that's cool. I mean, the other thing about performance is that you can, it's easy to tell if something is faster, right? Even on a small piece of software, you can tweak the algorithm, make it faster, and measure that it's getting a little faster. So people get very excited about that, and they can see immediate results from some performance hack, whereas writing cleaner, maintainable code is sort of a longer term thing that takes a while to realize if you've done a good job.
Yeah, we talk now about performing languages like C and C++, but what about the trade-off between performance and readability in general, even within one programming language? Because if I just, I don't know, retrieve something from a database, the code will be really clean. But if I use a cache, which might be more performant, the code will already be a little bit more complicated because I have to check if it's already in the cache, and then I get it from the cache, and otherwise I get it from the database. So is there always a trade-off between performance and code quality?
Well, there almost always is. So I know it's nice to think that a cleaner algorithm is also more efficient, and there occasionally you get something like that where you really do something clever and it's both shorter, easier to read, and runs faster. But in most cases, yes, performance is fighting against cleanness. Donald Knuth has this famous quote that premature optimization is the root of all evil. To me, I'd just say that optimization is the root of all evil. Almost all ugly code is because somebody was trying to optimize for performance. Now, it doesn't mean you never do that. The original quote, I think, is money is the root of all evil. And it doesn't mean that you should never have money. It just means that it causes other problems. And same thing with optimization. You have a nice, clean design, and then you say, oh, as you said, we need a cache, or we need this sideband API so we can special case this, or we need some more parameters to indicate this. And it all just complicates your design and makes your APIs harder to understand and harder to use. And so in general, essentially, you can always say, don't do performance optimization. Just as there's cases where you might be in a car accident where you get trapped by your seatbelt, and for some weird situation, it would have actually been better not to have worn your seatbelt. That doesn't mean you don't wear your seatbelt all the time, because it's generally better. So there are cases where you need performance optimization, sure, but it's much better at a broad level just to say, no, you don't need it. Forget about performance optimization. Just write your code cleanly. And then if it really turns out there's an actual bottleneck that actually matters to users, then you could dig in and start to make stuff uglier for performance reasons. But doing it because you just think it's clever or it might be slow, I'm going to do this little ugly hack for performance, is a bad idea. And unfortunately, as I said, I think a lot of people still feel that, oh, no, performance is critical. And if you don't understand the performance of your code, then you're a bad programmer. And I respectfully disagree.
Yeah, I think you made a really great point about the measurability, that if you can measure it quicker, then you get this immediate reward. Like, yeah, I saved 10 seconds. Whereas clean code, it's just a longer reward. So I can totally feel how that is one of the reasons that people tend to focus on optimization, because it just feels a little bit like a game or a puzzle.
Right.
How quick can I get this?
Even some of the coding standards, I mentioned a book. I once worked on this piece of software where somebody decided that all the header files, this is back in the C days, all the header files had to be alphabetized in order in the program, and which meant that we had to do this complicated system that basically any header file could include any other header file, because you never knew where it was going to show up in order. And that's the kind of thing, I'm sure it felt great. Like, oh, wow, I got them alphabetized. That just looks so neat in the code. You know, it's like, flossing your teeth or something. It just feels good. But I mean, it really was a negative, and yet you could do it and feel like you were doing something positive for the code, and get, like you said, this sort of immediate look how neat that looks. And maybe programmers are a little bit prone to that because they like to do clever things.
So you have made some comparisons between software and other things in this interview, and you also do that in the book. For example, of course, we talk about software engineering, and you have this example of when we build a bridge. And one of the other metaphors you use, which also came up in the show, is programming as medicine, that if you want to become a doctor, you need to have certification. You cannot just say, oh, I opened my own doctor shop today. Do you want to have an operation? I can do it without any certification. Those things are illegal. And software is way different, where many people become programmers. They don't even have a degree in computer science. They have a degree in something else, or there's enough of a market pool where people without a degree but with some talent or interest can also get into programming. What are the effects of that?
Well, I think that in one sense, it's great. We need programmers. So if you can be a music major and still be a good programmer, let's hire you. But it's still sort of weird that works. As you said, you don't have doctors who didn't go to medical school. Now, 200 years ago, you did have doctors who didn't go to medical school. They just follow a doctor around for a while and kind of pick up stuff, and then they'd go off and start practicing medicine. But eventually people said, no, we don't want that. Yes, it might give us a few more doctors, but we'd rather have trustworthy medicine instead. And I think software may eventually get to that point where people really insist on some sort of formal licensing for developers. Because right now you hire somebody to be a doctor, to be a programmer, and you really don't know what you're getting. It causes difficulty in interviewing when companies are trying to hire people. Somebody having a computer science degree could mean all sorts of things. So you wind up with these programming question interviews and stuff, which are very subjective. There's no equivalent of having a medical degree. And also just means that there's no standard to aim for. Universities don't know a set of skills and knowledge that they should be teaching that would match what industry had decided was the proper skill set. So it just caused a lot of inefficiencies in the system right now, that you don't have any kind of formal certification for something which is becoming so critically important. for the world. And unfortunately, a lot of security issues, for example, are basically caused by the weakest link in some long chain. So you don't need your software, if it just has one weak spot, you could have a security breach, and it might be that one programmer who didn't have proper security training, let's say, who wrote that code, and that's what lets you be exploited, even if the rest of your code is very solid. So it's very important that everybody know what they're doing.
So why do you reckon we don't have certification? Is it because we're too young?
I think it's because we're too young. There have been attempts at certification. There have been attempts to publish bodies of knowledge for computer science or software engineering, but there's just not enough agreement on what should be taught. There's this sort of gap between industry and academia that I talk about in the book. About they really don't talk to each other about what we'd like you to teach and what we need when people graduate, and how what's missing from the academic side. Talking to industry, saying what do you feel is missing in the people that are graduating. But yeah, right now, if you look at some of these bodies of knowledge, it's just sort of a long list of things people have come up with about software, but it's nothing that's been demonstrated or shown empirically to be the actual skills you need. And it's also kind of too broad. It's just a laundry list of things about software. And so you really need to figure out the core skill set before you could actually start licensing people. And I think industry is also worried. The computer software industry has kind of gotten away with not being liable for software problems. Some of that is probably fair because software is complicated and isn't as well understood as other things. But I think also industry is just saying, well, if we have licensing, that means we could be sued if we don't hire licensed engineers, but also just has the implication that, okay, now there's licensing, that means that there's expected levels of quality that would be produced by licensed engineers. And if we don't meet those, we'll be more open to lawsuits. So I think there's that particular issue is also, it's causing pushback from industry. But I mean, that could be overcome. You could just say, well, that's great, but we're still going to have licensing. But you'd have to set it as a future target that everybody worked towards. Not, you couldn't just impose it tomorrow because there wouldn't be a correct body of knowledge to actually license on.
So what you're saying is what it would entail to have such a certification is a deeper understanding of what are the skills needed to be a professional software engineer. Is that a good summary?
Exactly. You need agreement between industry and academia, and also just more awareness of what really matters and what doesn't matter, what needs to be taught in school, what could be learned on the job, that sort of thing. Because I think industry is more interested in people knowing specific languages. Like they'd probably say, oh, well, every school should teach JavaScript. That would be great. But I don't think that's necessarily true. That's just one specific language. I'd rather universities focused on slightly higher level of knowledge. So right now, you'll be hard to get agreement on something like that.
So let's look at current developments in the industry then, because your book paints sort of a bleak picture, saying that, we had bugs 40 years ago, 30 years ago, and basically we still have lots of bugs. Do you think that the software industry hasn't gotten any better in terms of code quality?
Well, it's gotten better. I think that it's gotten better. The languages have gotten better. The tools have gotten better, but also the software being attempted is more complicated. So I think we've stayed at about the same point on the human difficulty scale. People are still writing software that's slightly more complicated than they really should be trying with their current tools and skill set, which was true also sort of throughout the history of software engineering. So yes, there's a lot more software and better software, but you still have problems because the software is more complicated and people are more dependent on it. If you look at the history of software engineering, which I talk about in the book, there's been this search for quote unquote silver bullets, which is from an essay that Fred Brooks wrote called No Silver Bullet. And his point was there will never be one magic solution to the problems of software. It's not going to be only object-oriented programming or unit testing or TDD or Agile or DevOps or functional programming or whatever. And yet people keep looking for this. And I think we're still on that train where something new comes along, like DevOps and functional programming today, and everyone says, oh, finally, this will solve all the problems of software. We could forget about all that other stuff. And really, those things are useful in certain situations, like all these other previous silver bullets, but they're not a magic cure. And people are still looking for that magic cure. And until we can get past that and recognize that all these things are useful in their place, we'll probably still be stuck with people not really thinking, okay, how can we fundamentally make software engineering into engineering? They'll just keep chasing the latest shiny object that promises them a solution.
Why do you think people keep falling for those silver bullets? I mean, we are allegedly all very smart people.
Well, it's just really enticing to think, wow, if I just do this one thing, my problems will be solved. I think that the alternative, which is, okay, you just have to learn a lot more. It's kind of nice to be able to teach yourself programming in high school and then just have that carry you through a successful career. But unfortunately, that's not the way it has to be in the future. You're going to have to learn more in school. You're going to have to learn more during your professional career. Harlan Mills, I think 40 years ago, who was a programmer, worked at IBM and manager at IBM and wrote a lot of insightful things about software, made a comment like that the next generation of programmers is just going to have to learn a lot more and work a lot harder than the current generation did, because the problems are getting harder. And so I think it's nice to think that there's an easy solution. It's very tempting. There's a big industry out there that is pushing easy solutions or single solutions, but I don't think it's going to happen. Software is just too complicated to have one magic thing suddenly make it easy.
But if there's not one magical thing, at least there must be something that we can do, right? Do you have any ideas how we can improve?
Well, one thing that's helping is the move to the cloud, because some of these old wives' tales about software are actually now testable. When you have to maintain the software, you have to operate it, keep it running, rather than just write it, compile it, and throw it to your customers and let them deal with it, which was the way it was in the packaged software days in the 90s. You feel some of the pain of bad software immediately, and you realize, oh wow, this software is really hard to debug, or this bug happened because people didn't understand the code, or we had some test gap, or whatever. There's some process that wasn't followed. And so it's not a magic solution either, but it forces a little more focus on quality, because you feel the pain more directly. So hopefully the move to the cloud will cause and is causing some re-examination of what quality software is. And looking forward, if you talk about microservices and auto-scaling microservices, hopefully it'll put to rest some of this performance concern as well, this pre-optimization, because if you have a microservice that auto-scales, you really don't have to worry about performance, except in very rare cases. And you could just make a nice clean design, let it scale as needed in each individual service. And the performance things, as I said, it's probably not going to happen, but you see them happen gradually. Your customer base grows, you see some looming performance issue, then maybe you could address it then. So I think the cloud pushes software engineering in the right direction, even though, again, there'll still be problems and software will still be hard.
Yeah, because what exactly is the role of the cloud there? I can have terrible software and put it on the cloud and it still be terrible.
Right, it's terrible, but then you realize it sooner, because it's not just like, oh, I got a couple of phone calls from customers about our terrible software. It's wow, my website crashed and my database just fell over and nobody could order anything, and so you really realize, like, you're losing money and you're losing customers much more immediately when it's cloud software than when it's packaged software that's running on their computers.
So it has to do with the feedback cycle being shorter.
Yeah, the feedback cycle is shorter, or sort of immediate. When it crashes, you realize it hopefully immediately. So yeah, that does help a lot. Just having that shorter feedback cycle helps a lot with pushing people to care more about code quality, which at least it's a start. Maybe they don't know exactly how to get to quality code, but at least they realize more that it's an issue.
Yeah, but one of those people that is famous for putting stuff on the cloud actually seems to have almost the opposite slogan, because Facebook famously says, "Move fast and break things." Isn't that the opposite of code quality if stuff breaks?
Yeah, I think that's overstated a bit. I know I talk to people at Amazon since I live in Seattle, and they want to deploy rapidly. They sort of bias in favor of shipping versus not shipping, but they also have very good rollback tools. And Amazon has such volume, and a company like Facebook also, they can just say, okay, our sales are down 10% over what we expect based on historical data. There must be a bug in our latest deployment, and they can roll it back. They don't even care what happened. They just know that if people aren't clicking on the buy button as much, something is broken. So they have the volume where they can do that. So that allows them to bias heavily towards shipping, because they also they can detect the need for a rollback very quickly. And most companies don't have that scale. So I think this slogan about move fast and break things, I think that sounds great to people coming out of college they want to hire, but it's really move fast and don't be super concerned about breaking things. It's not a goal to actually break things as some measure of positive activity. It's just because they can fix things quickly, they don't worry so much about quote unquote breaking them.
Yeah, so it has to do with the tools, also maybe with how much grip you have on what's going on. So let's talk about that a little bit more, because you already said before, I will notice if something is wrong because my website crashes or my database falls over. But one of the other examples of benefits of putting stuff in the cloud is you can have automated tests and automated metrics and calculating everything even before it breaks down. Do you think those are the solutions? Or is it just let it break or crash, and then if we have good tools to roll everything back, it will be fine?
Well, no, I mean, of course, a company like Amazon has multiple layers of detecting. They're looking at clicks at the end, but they also have looking for API failures internally, and they have all these metrics they look at to say, okay, well, it looks like something's wrong here. And their stuff is segmented into services so they can deploy and roll back individually. So, oh yeah, no, I mean, it's a whole chain of things. It's not just put it out there and wait until the users feel some pain, because in the end, I mean, somebody is not able to buy something. Somebody's having a negative experience if you let it get that far, even if you've only rolled it out to a small percentage and all that. You're still making somebody unhappy. So yes, you want to check. You have internal testing, automated testing, all these layers before you put it out. I think the nice thing that's happening now is a lot of that is automated, so you can run through a bunch of testing very quickly and deploy it. You're not waiting for a person to run through the website manually and make sure it works. So you can deploy it very quickly and very frequently without having any extra number of people involved and having the human delay and possibly somebody not doing the test exactly right and missing a bug. So yeah, no, it's a whole chain of things, not just throw it out there and wait for errors.
Got it. So, do you have examples of errors that you would not be able to find in that way? Dijkstra famously said, which is also in your book, is that testing can only show the presence of errors and not the absence. So, if we deploy stuff, how will we know about those things we don't know about?
Right. Well, I mean, in the end, yes, you might have some error that is in some esoteric case that you don't find with your testing. So no, Dijkstra's right. I mean, in the end, you if you find a bug, you know it's a bug. But if you don't find anything, it just might be because the bug is well hidden. But of course, the more obscure it is, the less likely it is to hit. So the number of users affected is less. So you might not have to roll back for that. Maybe it's something you can fix. And of course, companies are investing more and more in more automated testing. So Dijkstra wasn't really thinking about automated testing. He was thinking about manual user testing. So the scale of what a test could do has grown a lot since he wrote that. But it's still true. I mean, he wrote that in the 70s. Harlan Mills said the same thing in the 70s. Despite that, Microsoft rediscovered testing in the 1980s and spent 15 years relearning the fact that, yes, you're right. Testing doesn't find all bugs. You can't test in quality. You need to work on designing in quality. It's sort of a problem with the industry that because people aren't looking back historically, they tend to spend a lot of time reinventing things that were actually already known if they had been paying attention.
I think that's a great way to close the show, because one of the things you could do if you want to pay more attention to the history of software is to read your book, because it has lots of great examples of old bugs that people might not be aware of and strategies that have been tried. Thanks a lot for being on the show. Is there anything you wanted to add before we close off?
No, just to say thank you very much for having me.
Awesome. So we'll make sure we put a link to the book in the show notes. Do you have a website? Are you on Twitter? Are there other places where people can follow you?
I'm on Twitter, Adam David Barr. I'll send you a link. I don't tweet a ton, but it is a way to get a hold of me.
Cool. So we'll put that in the show notes as well. Thanks for being on the show.
Yes, thank you.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.